Hi, today I'm going to discuss the solutions for Atcoder Beginner Contest 377 Problems A to E. Let's look at Problem A. For Problem A, we have a string and we need to check if the string can be rearranged to become the capital letters ABC. And let's look at the code for this problem. If a string can be rearranged, then we only need to check if A, B, and C each occur in the string once. So this part, we first input the string and then we just loop through the string to check if each character occurs once. And if they each occur once, then the answer is yes. Else, we can't form a rearrangement to have ABC. Let's look at problem B next. For this problem, we have a grid of 64 squares with 8 rows and 8 columns. And some of the grids are already occupied by pieces, and we need to count the number of empty squares that can't be captured by any of the other existing pieces. So if a piece is placed, then it can capture any of the pieces that are placed on the same row or the same column. So for this example, this piece can capture any of the other pieces that are placed on row 4 or column 4. For this problem, since the grid is small, we can just directly loop through the entire grid and check which of the places are already occupied by a piece. Then we can mark all the rows and columns that are occupied by that piece as non-empty. And afterwards, we can just loop through the entire grid and count which of the squares are left. Let's look at the code for this problem. We first input the grid, and then we create a 2D array possible, which represents whether the current square can be captured by any of the other pieces. So initially, every square is empty. So afterwards, we loop through our grid and check if the grid is occupied. If the grid is occupied by another piece, then we update the possible array. So for each row and column that the piece is on, then there isn't any space for a new piece. So we update the possible array to false for that row and column. And afterwards, we loop through the entire array and check if which of the locations are still empty, which means that they can't be captured by any of the other pieces. If they're still empty, we increment the answer, and afterwards, we print out the answer. Problem C is similar to problem B, but now the grid has n rows and n columns, and n can now be up to 10 to the power of 9. There are m pieces that are placed on the grid, and this time, a piece can capture any other piece that are on each of the 8 squares marked in blue. And this time, we can't just loop through the entire grid because the grid is too large. And however, we notice that there are only m pieces, and m is only up to 2 times 10 to the power of 5. So we can just loop through all the pieces and count the number of grids that can't be occupied. So let's look at the code for this problem. For this problem, we input the locations where the grid is already occupied, and For each piece, it can capture any of the pieces that are listed below. So we just need to add all of these locations into our set. And afterwards, when we compute the answer, our answer would just be the number of squares in the grid subtracted by the number of squares that can't be occupied. So for the add function, we need to check if the x and y values are still in the boundaries of the grid. If they are, we can insert them into the set, which will ensure that each square is only counted once. Afterwards, the number of squares that can't be occupied will just be the size of the set, and we can just subtract that from our answer. For problem D, we have n segments that start with L, Li, and end with Ri. And we need to count the number of pairs of integers Lr with L and R both less than m that don't completely contain any interval. For this problem, we can't simply check all of the pairs and see if they satisfy the conditions, because that would take all m squared times n time, which would be too large. So we need to think of how to further reduce the time complexity. Let's first look at a sample input. So if the L endpoint starts at 1, then R can be up to 5, because if it goes up to 6, then it would include the first segment. And if we move L to 2, then now it already doesn't include the first segment, so R can move up to 10, because otherwise it would include the second segment, which ends at 11. And if we further move L to 5, then now it doesn't include the second segment. So the R endpoint can be up to 11. And so we notice that we can sort these segments by increasing order of their left endpoint. And then we can loop through all the values of L from 1 to m, and then increase the answer each time by the number of possible values of R. So for each L, R can be from L to R max, where R max is just the minimum right endpoints for all the segments that have the left endpoint that is greater than our current value for L. So what this means is just when the L endpoint is at 5, then for all other endpoints that have L values greater than our current L, which is just any other endpoint that have their left endpoint greater than 5, then we need to find their minimum right endpoint. So for this case, when L is 5, then any other segment that have their L endpoints greater than or equal to 5 would be included in our segment. So we find the minimum R endpoint for all these segments, which is just 11 for this case. For this problem, we first input all these segments, which we have to store in pairs because we need to match each of the L endpoints with their R endpoints. And afterwards, we sort all these segments based on their L values. And min R would store the minimum R endpoint of the current segment to the last segment. So min Rn represents when L already doesn't include the last segment, then R can still be up to M. So it would store M plus 1. And afterwards, for each I, we will update min Ri as the minimum value of the current segment's R endpoint and all the R endpoints after it. And for this loop, we loop through all the possible values of L. And J represents the current segment that still has its L endpoint that is greater than or equal to our current R. So for this loop, if the J endpoint has a L value that is already smaller than our current L, then we will increase it. And afterwards, this part updates the answer, which just adds the number of possible values of R for our current L. And this would just be min Rj minus I. For problem E, we have an array P, and we need to perform an operation k times to update pi to ppi. And we need to print out the array P after all the operations. So k can be very large since it can be up to 10 to the power of 18. So we notice that we can't directly just perform all the k operations because that would exceed the time complexity. For this problem, we can create a directed graph with edges I pointing to pi. So for the sample input, the graph would look like this. And we notice that initially P looks like this, and after the first transformation, each of the locations shift by 2 places. So initially 5 is on the first location, and then the first location now has a value of 2, which shifts by 2. And afterwards, for the second location becomes 4 after the first transformation, which also shifts by 2. And so we notice that after the first location, each of the p values shift by 2 locations on the graph. So let's look at the second transformation. For the second transformation, we notice that each place shifts by 4 places on the graph. So the first location now has a value of 4 after the second transformation. So we notice that this is 4 steps away in our graph. And for the second place, after the second transformation, the value becomes 5, which is again 4 transformations, as shown in the graph above. And afterwards, for the third transformation, we notice that each of the values shifts by 8 places. So the first location in P becomes 6, which is 8 places away from its original one. So from this observation, we notice that the kth transformation will shift all the answers by 2 to the power of k. And we would first try to solve this problem by binary lifting. However, this wouldn't work because 2 to the power of k is too large and would exceed the memory limit. And however, we later noticed that the graph can be decomposed into several cycles. And for each cycle in the graph, the answer will just shift by 2 to the power of k and modulo the length of the cycle. So for this problem, for example, for the third transformation, the graph would shift by 8 places. However, since the length of the cycle is just 5, then this would be equal to just shifting 3 places. So for the first location, if we shift 3 places, it would become 6. And for the second location, when we shift 3 places, it goes to 1. And so we can just find all the cycles by doing a DFS. And for each element in the cycle, we update the answer by shifting the value to 2 to the power of k divided by the length of the cycle. We first input all the values for p, and then for this part, if the value hasn't been visited yet, then we do a DFS. And for the DFS, we push all the values into a vector that stores our current cycle. And we also mark the nodes as visited. And afterwards, the value we shift by for all the nodes in this cycle will just be L, which is 2 to the power of k modulo the length of the current cycle. And this power function just computes the answer for a to the power of b when mod, and afterwards we loop through all the values in this cycle. And for this cycle, we update the answer. For each node in this cycle, the answer will just become the answer while we shift L places in the graph. And afterwards, we just loop through all other nodes that haven't been visited yet and repeat the current process.